Hi, everyone. My name is Kwangjun. I'm a PhD student at MIT, and I'm going to talk about learning threshold neurons via the edge of stability and sharpness-aware minimization. This talk is based on the following two NeurIPS paper that I'm going to present this year. So let me start this presentation by a very important question, which is how do neural networks learn to generalize? And one possible explanation people often have is that during training, neural network discovers useful structures for generalization. One prominent example is this edge detectors in convolutional neural networks. And in order to understand how these edge detectors arise, we're going to study a simple concrete model called sparse coding problem. To define the problem, let V1 up to Vd be a fixed but unknown hidden basis in Euclidean space. Then the sparse coding problem is nothing but the binary classification problem of x and y pair, where x is defined as lambda times y, which is plus minus one label, times vi, one of the bases, plus noise. So if there's no noise, this classification is relatively straightforward. But with the noise, we need to somehow figure out the way to threshold out the noise to recover the signal in order to classify the example. One concrete way to consider to do this classification is the following one hidden layer neural network defined as this. So the intuition is that if B is sufficiently negative of order negative square root log D, then this ReLU network will play the role of the thresholding operator. So given this target network, the natural question is, when does gradient descent on this parameterized architecture converge to something like the target network? And it turns out this question requires something, some new understanding of optimization. So to showcase that, let's even further simplify. Let's consider a case where we know the basis V1 up to Vd. In that case, we don't have to learn the first layer weights. And let's say we simplify the problem such that we only have to learn this outer layer weights, A plus A minus, and the share bias B. So it's like an embarrassingly simple three-dimensional optimization. And let's see how GD works for this very simple three-dimensional optimization problem. So I'm going to plot the training loss and the bias value B, and then second layer, sum of the weights, A plus plus A minus. When the learning rate is sufficiently small, you see that training loss is going down, but then bias doesn't move. And same thing is true for when you increase the learning rate by 10 times. But when you increase the learning rate by another 10 times, something bizarre happens, where loss is going down non-monotonically, and bias finally moves, so thresholding operator or edge detector arises, but in a very unconventional way, in such a way that the weights are oscillating, as you can see from the third plot. So it seems that the thresholding units arise with large, unstable learning rates. All right, so what's going on? A more striking phenomenon occurs when you try to plot the final bias and test accuracy as a function of eta. So what I'm showing is the final bias after the training as a function of learning rate eta, and also corresponding final test accuracy after training. And as you can see that we indeed need a large learning rate to learn the final negative bias, which leads to better generalization. Okay. Another striking plot point of the plot is that there's phase transition. I'm going to revisit, but it turns out that phase transition, the green line, vertical line, is at step size A pi over D squared. And this is not, these striking phenomena is not specific to this simple model. So for the original network of training all the weights of the one hidden layer neural network, we also see the phenomenon where test accuracy is better with the large learning rate, and large learning rate leads to bias, negative bias, which leads to thresholding units. And to a certain extent, we see that for the resonant 18 on CFAR10. Okay, so the main question of this work is that what is the role of large learning rate for this learning negative bias or learning thresholding units? However, as we saw from the previous plot, in order to understand this question, we need to understand something fundamentally new, which is this instability or unstable training dynamics. So do we know anything about this unstable behavior? It turns out there's a growing literature on understanding unstable behavior of gradient descent for training neural network. So to summarize that, most gradient descent analysis assumes a condition that step size has to be sufficiently small. By that, it has to be smaller than 2 over large eigenvalue of the Hessian. But then this great work by Jeremy Cohen et al. From 2021, iClear, showed that in neural network training, we often see that this condition breaks. So for illustration, they call it edge of stability phenomenon. So in the plot I'm going to show, sharpness means the lambda max value of the Hessian. And as you can see that sharpness value rises up and actually goes beyond this 2 over eta threshold. So it turns out this edge of stability phenomenon that was observed in this empirical work of Cohen et al. Is actually what we need for understanding sparse coding problem, because whenever we see this bias decreasing with this unstable dynamics of oscillation, we also do see that sharpness going up and saturates at the threshold. So we first need to understand training dynamics of edge of stability in order to understand what's going on with this large step size phenomenon. However, our theoretical understanding of edge of stability is limited. In particular, Cohen et al., the work by Cohen et al. Is empirical. So we first gained some intuitions about the working mechanism of edge of stability based on simple examples. And in particular, we consider this very simple 2D non-convex function, xy to L of x times y. More specifically, we consider L to be convex, even, and Lipschitz. And it's because of the parameterization x times y that this function is non-convex. So, here's the dynamics of GD on this function. So recall that it is L of x times y. So and L is minimized at 0. So this function in the xy plane is minimized at x-axis and y-axis. And you can, in terms of the geometry of the landscape, as you get further away from the origin, the minimum becomes sharper and sharper, as in like landscape. And as you get close to the origin, minimum becomes flatter. So when you initialize gradient descent on the upper plane, it turns out the gradient descent will converge to gradient flow, the continuous dynamics converges to this value. But then when you choose the step size sufficiently small, then gradient descent will track this gradient flow dynamics. But when you choose a step size sufficiently large, as in it goes beyond the edge of stability threshold, it turns out something interesting happened. Gradient descent dynamics tracks the gradient flow up until it hits the y-axis and it starts oscillating, and which leads to decrease in the y value, and it converges there. Through careful analysis, we're able to prove this mathematically, and we show that if the step size is smaller than some threshold, which is actually edge of stability threshold, then final bias is equal to the value that gradient flow converges to. On the other hand, if step size is larger than the edge of stability threshold, then gradient descent converges to much smaller y value with a lot of oscillation. And we were able to characterize the limiting value up to O eta error. Okay, so let's get back to our original question. Now we have some understanding of edge of stability. Then how are we going to answer this original sparse coding problem based on this L of xy? It turns out L of xy is in fact all we need to understand the sparse coding problem. It turns out when you plot the dynamics of this A minus plus A plus against the bias value. Turns out that dynamics looks like this, which is very much reminiscent of this L of XY dynamics we just saw earlier. So it turns out, again, L of XY is all you need to understand. And here's a theorem. And the proof technique is built upon our proof technique for the L of XY, and which shows that this exactly the value that I showed you earlier. If step size is less than a pi over d squared, then the limiting bias value is very near zero, because 1 over d squared is a very small value. And when its step size is beyond the edge of stability threshold, a pi over d squared, then limiting bias is strictly negative. In particular, let's say if eta was 10 pi over d squared, a slightly above the threshold, then negative value, the limiting bias value has to be smaller than the strictly negative number. Okay, so let me move on to the second part of the talk. Beyond edge of stability, and I'm going to talk about some flat minima optimization. So flat minima optimization is very popular technique in the modern machine learning optimization. So here's the experiments for the sparse coding that we saw earlier. So large learning rate leads to better generalization and more negative bias or thresholding units. So the dilemma here is that generalization occurs with carefully chosen unstable learning rates, which is not really desirable for practitioners, because you basically need to choose the learning rate as large as possible before it diverges, which requires some tuning. So can we do that more intelligently? And that's the precise scope of the flat minima optimizer. One of the most popular flat minima optimizers is something called SAM, which stands for Sharpness-Aware Minimization. And as an overview, I want you to focus on the solid lines, blue, orange, and green lines in the plot. And you can see without careful tuning, the thresholding units always arises, which leads to better generalization. So what is SAM? So SAM is the optimizer developed by Foret et al. In published in iClear 2021. It's kind of like an add-on feature that encourages the base optimizer to find flatter minima. And it got a lot of excitement because it achieves a lot of state-of-the-art generalization in standard benchmark problems. So I told you that it's an add-on feature for any base optimizer you choose. And if you choose GD as a base optimizer, it looks like this. So instead of taking the gradient step, you collect the gradient from one step of normalized gradient ascent and collect the gradient and use that gradient to do the descent. It's quite bizarre. And in particular, if rho is chosen to be 0, then it recovers just standard gradient descent. There have been a lot of theoretical works, but there's one curious aspect in these theoretical works is that, so original inventor of SAM emphasized the normalization term in the ascent step. And in fact, two theoretical works, first theoretical works, actually make use of this property, improving their theoretical properties. However, the subsequent work after these two works kind of start to omit the normalization term for simplicity in the analysis, and instead consider this unnormalized SAM, where instead of doing the normalized gradient ascent step, they omit the normalization term. So what's going on? So since I have a very limited time, I'm gonna just briefly summarize what our main result of the second paper is about. So again, I recall the dilemma of tuning the step size carefully for generalization. And it turns out normalization is a step in SAM, precisely copes with this issue. So I again recall the plot. So now when you see the USAM, you also see the dilemma where you have to tune the step size carefully to get better generalization. On the other hand, SAM with the normalization step, without carefully choosing step size, we always see better generalization and negative bias, hence edge detector. So the main takeaway of the second work is that the normalization step helps with the stability, and that leads to we don't have to tune the step size carefully. And also we show that regardless of whatever step size eta or rho you choose, SAM, because of the normalization step, will always take you to the flattest minimum. All right, so I arrive at the conclusion, my last slide. So we present the first explanation for the emergence of the threshold neuron in models such as a sparse coding model. Surprisingly, the answer is tied with the interesting phenomena observed in the literature called edge of stability phenomenon. And also investigating this with the simple model let us understand the modern optimization techniques like sharpness-aware minimization. Thank you for listening.